Let's
Okay.
stuff you can verbalize?
Yes, sir.
Okay.
Okay, so first one is, it says find the derivative of the function f of x equals x to the sixth, parenthesis 4 plus 5x, and that is all to the fifth.
Like that?
Yes, sir.
Or the whole thing is to the fifth?
Yeah, it's like that to the fifth. That's perfect.
Okay. So, what are we going to use here to do this?
Okay, so I thought it was kind of a mix of the power rule and the product rule.
Correct. And the chain rule.
And the chain rule, so then you have to do, like, multiply it all by 5, which is the derivative of what's inside of the parentheses,
Exactly.
correct?
Exactly.
Okay.
Well, let's start and methodically go through it piece by piece. Now,
Okay.
since the product rule can be done in either order,
Yes.
I always suggest people start there.
With x to the sixth, yes.
Well,
Perfect.
start with that function, not the derivative of that function.
Right.
Because it always gives you the same starting spot. It's an easy starting spot, and then you're doing it the same way every time.
Perfect.
Now, so the next thing to do is to take the derivative of this second function.
Which is 5 times 4 plus 5x to the fourth.
Uh-huh.
Okay.
Times
5.
Correct. Got to apply the chain rule. So
Perfect.
that 5 out there for the moment.
Okay.
And then it's adding. That's why it didn't matter which we did first.
Right.
What's the rest of it?
And then it's 5x to the fifth, or 6x to the fifth, times 4 plus 5x to the fifth, that function.
Right. Now, there's a little bit of simplification. And you'll notice there's some factoring that could be done if there was a reason to do it. I could take out at least 4 plus 5x to the fourth from both of these terms. But there's no need to do it because there's no denominator. As opposed to when you use the quotient rule. When you use the quotient rule, you always have a denominator, and then very frequently you can factor out a binomial term from the numerator and the denominator and simplify it.
Okay.
Okay?
That makes sense.
But with the product rule and there's no denominator, there's no real reason to go to all of that work. Certainly I'd want to turn that into a 25. And that's not all I can do. I can't distribute anything or anything. So that would be your answer.
So it would be 25x to the sixth times 4x, that function, plus 6x to the fifth, that function.
Uh-huh.
Okay.
Exactly.
It seems to me that they simplified it.
Do you have the answers on these?
I do. This is a multiple choice problem, so I have multiple answers.
Oh, interesting. So what are their multiple answers?
They have, like, this is just an example. Let me tell you the one that they actually wanted.
Probably send a picture of it to me. That'd be better. Because I'm trying to figure out how you could possibly simplify this. You could also factor out x to the fifth.
That's I think what they did. They have x to the fifth times 4 plus 5x to the fourth times 24 plus 55x as the answer.
Yeah. Hold on. Read that again. They factored out the x to the fifth.
X to the fifth times 4 plus 5x to the fourth.
Okay.
Then all that is multiplied to 24 plus 55x.
24. Where are they getting the 24? You mean 25?
They say 24. It's just 24. That's all it is. Plus 55x. And I did this problem without looking at the key, and I got your first answer. That's what I got. And then I looked at all of their options, and they simplified it in a certain way that I couldn't follow.
Can you send me the picture of it? Because
yes.
This doesn't seem right to me. In other words, if I do factor out an x to the 5th, what I have left is, first of all, 25x.
Okay.
And then I have plus 6. Now I'm seeing where they get the 24. Yeah, see, that becomes to the 1 power. Now they distribute it, so they do simplify it. Now I see it.
Okay.
Yeah, there is a reason to factor it out. Because, of course, you could always have done that. It just would have been very laborious to take that binomial to the 4th power.
Right.
But by factoring out that 4 plus 5x to the 4th, I left a 4 plus 5x, which then could be simplified and combined with the 25x.
Okay.
In other words, that whole thing now should be x plus 24. Now, hold on, let's see. And now that becomes x to the 6th. No, hold on. That's the fun of calculus, is the algebra. The algebra is frequently the most tough part by a lot.
Right. Right.
Okay.
And I feel like my teacher would maybe take a point off for this, you know?
Okay. Yeah.
I don't think it would be anything too ridiculous.
Well, here's the question I would have. Why don't we just expand that, and then we could simplify it? In other words, I can technically expand 4 plus 5x to the 5th, and then I can distribute it with a 6x to the 5th. I can do the same thing over on the left. It's just we don't do it because it's so much work. We leave it in this format.
That's what I was thinking too. It's just unnecessary work to simplify it down to a slightly simple.
Now, the one advantage here is that once you do take that out, you're left with 1 to the 1 power, and then there's no work to do to distribute it. So yeah. I can kind of see the rationale here. But what if this was to the 6th? Then you wouldn't do it.
Right.
Because then you'd be left with a 4 plus 5x squared, and I think they would expect you to expand that.
Right.
So, I don't know.
Okay.
These
but I get it.
Choices can often be more difficult than non-multiple choices.
That's what I'm saying. Yeah, exactly. So, but that reassures me that I did the initial problem correctly. Yeah. You taught me in a way to where I initially did that all and got that first answer. Yeah. It's just the algebra behind it. That's where I just didn't get it.
Well, and it's not always that clear either. I couldn't see, the first time I looked at this, I could not see what the advantage of factoring that 4 plus 5x to the 4th out. Because I wasn't looking one step forward. That's going to leave a 4 plus 5x to the 1. And do more easily. So.
Exactly. And yeah, I mean, that would only, it's a derivatives test. It's not an algebra test, you know? So like the fact that I found the right derivative.
Believe it or not, hard derivatives become more algebra than they are calculus. Seriously.
Okay.
Especially when you get the quotients. Wait till, and I'm sure we will, right? You've gotten the quotient rule, haven't you?
Yes.
You've had them all, yeah. Well, wait till we get to some quotients. You'll see some algebra where you end up having to factor out negative exponents. In other words, here's a problem that you might not be ever used to doing, where I have that, and let's say it's multiplied by an x, and then over here I have an x squared multiplying an x minus 3 to the positive 1/2.
Right.
Now, what you're not used to doing here is factoring out not only binomial terms, but binomial terms to the negative exponent is the best way to do it. You can technically factor out either one. You can factor out the x minus 3 to the positive 1/2, but you end up doing this a lot with quotient rule.
Okay.
Because you end up with a lot of square roots, which results in these fractional exponents, and so it's a factoring problem that you've probably never done.
Okay. That makes.
Let's handle that when we get to it, I guess.
Okay. So perfect. This next problem is, what is the slope of the tangent line to the curve 3y squared minus 2x squared equals 6 minus 2xy? And then it says at the point 3, 2.
Okay. First of all, this is not a function. It's a curve, but it's not going to pass the vertical line test.
Right, so it's not a function.
Yeah, I guess that's really irrelevant. But what is relevant is that you're not going to be able to solve this for y.
Okay.
I'm not sure what the algebra, no, I don't see a way to solve it for y without invoking some very complicated aspect of the quadratic formula. And you don't need to. This is what implicit differentiation was built for, is when you cannot solve a function for y, and yet you still need to differentiate it. Okay, we can still solve for dy dx. And basically what we're doing is this. I'm taking the derivative of the top side with respect to x, and I'm taking the derivative of the right numerator with respect to x. Okay, so let's go through it term by term. What's the first term going to be?
Okay, it's going to be 6y prime minus 4x equals, what is it? So then it would be 2x, it would be negative 2x times y prime plus negative, or minus 2y.
Perfect.
There we go. There it is.
Now, what's the next step? Because we're trying to solve for y prime.
So you want to get the y primes on one side, and you want to get all the y's and x's on the other side to create an equation that equals y prime?
Well, there's one other very important step in there.
Do you want to divide them all by a common factor?
Well, hold on, no. In other words, your first statement was absolutely correct. Get one side that has all the terms with y prime on there, and the other side with no terms with y prime. Now the secret here is factor out the y prime.
Okay.
Because that's going to leave something that you can then divide both sides by.
Right.
And you will have solved for y prime. So without rewriting everything, I'm just going to divide that by 6y plus 2x, and that's equal to y prime. Now, I can simplify that, and I will in a second, but notice how I can figure out the slope at this point that includes an x and a y coordinate.
Right. So then you just plug the y in.
Yeah, exactly. We're not used to having derivatives be functions of x and y. We're used to having them be functions of x and evaluating them at a certain x value.
Okay.
I don't even have to give you both points. In other words, had they just given us the x value, we could have figured out what the y value was from this original equation. But they gave us both points, and these problems, they usually will give you both points.
Okay.
Okay? So, first of all, let's do this.
Now, I'm also curious how you got the 4x minus 2y out of that. Oh, just kidding. Just kidding.
Okay, I was
You flipped the 4x
4x to the
2x.
other side, yeah.
Okay.
And
Yep,
this, I had a plus and a minus there, so it turned it into minus 2y.
Right, perfect. That makes sense.
Okay. Now, fill in the x and y value. What do you have?
So
6 minus 2 all over 9 plus 2, correct?
Right.
I hope I did my math right. 4/11ths. That's the slope of the tangent line. Now, how do I come up with the equation of the tangent line?
Then you just add that in and plug in the x and y values. So it's like y minus 2 equals 4 over 11 x minus 3, right?
Perfect. In other words, that's the point slope format. Different than the slope intercept format, obviously.
Right.
But with calculus, because you so frequently have a slope and a point, this ends up being used a lot more, point slope format.
Yeah.
Because you rarely have to worry about the slope, the y-intercept. We always have a point and a slope. The slope coming from the first derivative evaluated at that point.
Okay.
Do you have answers on all of these?
I do. Now, I didn't get 4/11ths for that answer.
You did not.
Well, it's just not an option.
These are all multiple choice?
These ones are, yeah, I have about 50 multiple choice problems.
Hold on a second. I wonder if in simplifying that I screwed up. That's what makes me think. Let's see, that was 2x, and I'm plugging in, what was my point, 3 comma 2?
Yeah. Yes, 3 comma 2.
3 comma 2, so let me do this math again. Maybe I made a mistake. And sometimes it doesn't pay to simplify, because I ended up with scratchy marks all over the page. So I got 12 minus 6, correct?
12 minus 6.
Oh, I know what I did. I put in the wrong y on the bottom, I think. I should have put in the 2 for y there. I bet I put the x value in. Plus 2 times 3, 6, yeah, I get 6/18ths, 1/3. Now, did they give you all the answers in point slope format, or did they give you some of them in y equal mx plus b format?
It didn't ask for the equation. It just asked for the slope.
Ah, okay. Did you get 1/3?
I have 12 minus 4 right now. 6y, that'd be 12 plus 4 is 16.
Whoops, I did it wrong the second time. It's 12 minus 4, excuse me.
I still got 2/3, and that's not one of them.
Well, now hold on. Yeah, but let me at least get my answer right.
Okay. Yeah, no, you're right.
Simple math errors. Let's see. The x-coordinate was 3. The y-coordinate was 2. So it's 12 minus 4 on top. On the bottom, it's 12 plus 6. So I'm getting 8/18ths.
Okay.
4/9.
Yep. I did, okay.
Thank goodness. Only took me 3 times.
I know, me too. That's what I'm saying. Simple math. 4/9.
Now, here's why I screwed up, and this is really easy to do. And that's because the x is on the left and the y is on the right in the numerator.
Yep.
Same way, x is on the left, y is on the right on the point. And then I go down to the denominator, and I just think that that's going to be the x value. So I got them reversed. boy, and that's a mistake that's easy to make and tough to catch.
Right, right.
Tough to catch because you don't think you're going to experience dyslexia in the middle of a problem.
Okay, I get it though, but perfect. 4/9, that's an answer. Got it.
All right.
Perfect. Okay, now this one, 23. What is the instantaneous rate of change at x equals 2 of the function f of x equals, and this is going to be a fraction, so in the numerator, it's x squared minus 2, and then that is over x minus 1.
Oops, x minus 1.
Yes.
It's just early in the morning.
Yeah, I apologize about that.
No, I didn't mean to say that with that. I love early in the morning appointments. I really do.
Good.
Because it allows me to distribute my day out.
Uh-huh.
Normally,
That is very
I'm looking at 5 appointments in a row from 3 o'clock to 9 o'clock, and that's hard to do for me. So I'm for one early, one around noon, one in the middle afternoon, another couple in the evening. That'd be the perfect day for me.
Okay, okay, I see. Perfect.
So they want the instantaneous rate of change is the same thing as the first derivative. It's the same thing as the first derivative at a point.
Okay.
Okay, so first of all, we got to get the first derivative. And I don't see anything I can do to simplify this thing.
Okay.
In other words, I can factor the top, but into x minus root 2 times x plus root 2, but that doesn't do any good. So, all right, so let's apply the quotient rule. We're going to see some of this algebra I've been telling you. Like that.
Right. Okay, so I got x minus 1 times 2x minus x squared minus 2. Then that's multiplied by 1, but...
Notice the importance of parentheses.
Yes.
You must use parentheses around virtually every term. I didn't have to put them around the 2x, but I did just for clarification.
Right. And then that's all over x minus 1 squared.
Okay. Now, no reason to spend a lot of time simplifying this, even though I can see that I'm going to have a 2x squared over here minus an x squared. I could simplify it. I would never give this as an answer, but the truth is that all I have to do is evaluate it at 2. So
right.
find f prime at 2, so why even bother to simplify it? Let's just substitute. So we get 1 times 4 minus 2 all over 1. There's less time to solve it than it would have taken to simplify it.
Right, exactly. So that's 2?
3.
3.
Excuse me. It's 4 minus 2. It is 2.
Perfect. Perfect.
Just adding those two.
That is an answer, dude. What I'm talking about. Nothing. Okay, now it says find the slope of the graph of the function at the given value.
Okay.
So the function is f of x equals negative 4x squared plus 7 over x squared. So plus, and then it's a fraction. There you go. And then it says when x equals 3.
Okay.
So find the slope of the graph of the function. Would that just be plug 3 in, or do I need to find the derivative?
Yep. Slope always means derivative.
Okay. Okay.
Tell you what, if you find a problem that doesn't begin with the first step of finding the derivative, you let me know. I'll bet you don't have very many.
Okay. Perfect. That's what I like to do.
You can just always assume that you got to take the first derivative when you're taking Calc A.
Okay. Okay. Perfect.
And first derivative has a lot of meanings. Instantaneous rate of change, slope.
Right. slope of the graph of the function at the given value.
Yeah, well, of course, that's what instantaneous means, is we're taking the slope at a point. See, prior to calculus, you were always figuring average slopes because you were taking the slope between 2 points on a graph, and you just could figure out the rise, divide by the run, and you'd have the average slope. You can't do that at a single point. There's no rise or run. So the only way to do it is to take the first derivative of it.
Okay.
Excuse me 1 second.
Bless you. So that can just...
All right. We don't want to use the quotient rule here.
We don't?
No, because there's an easier rule to use.
Okay.
And that's the power rule. As long as
which
I
would be
with a negative exponent, I
okay.
can avoid the quotient rule. Now it's super easy.
Right.
So what's the derivative?
So that would be minus 7x, plus 7x squared.
Hold on. It's minus 8x, correct?
There we go. Okay, so negative 8x minus 14x.
So what?
And then,
And then you got to subtract 1 from the...
Oh, yeah, to the negative third.
Yeah. In other words, it's fine to work with negative exponents because you can use the power rule.
Right.
But make sure that when you're subtracting 1 from a negative exponent, it goes to minus 3, not minus 1.
Right. Right. That makes sense. Okay.
And now, again, if that's f prime of x, what's f prime of 3?
You just plug 3 in, so then it would be...
Minus 24 minus 14 over 27. And then you can, I don't know what kind of answers you're looking at there. Can you figure out?
It's like 634 over 27, negative 634 over 27, like all that stuff. I can simplify that on my own.
Negative 634 over 27. Because I got to find a common denominator here. So it becomes minus 24 times 27 over 27 minus 14 over 27. So that's a negative number. I'm subtracting a positive. I'm going to end up with a negative number. And whatever 24 times 27 minus 14 is my numerator.
Right. Perfect. That makes sense. Okay. Awesome. Thank you so much. Okay. 25. Determine the points at which the graph of the function has a horizontal tangent.
Okay.
The function is f of x equals 8 over x minus 6.
We're looking for horizontal tangent. What does that mean?
That f of x equals 0 or f prime of x equals 0?
F prime of x. In other words, the original function, whatever it looks like, needs to have a horizontal tangent. Well, I can tell you right now, this one doesn't have it because that's hyperbolic in nature. So it's going to look like this. There are no horizontal tangents on that thing. And we're going to figure that out when we try to find it. Okay? So, again, you could apply the quotient rule, but the quotient rule means you're going to have more complicated algebra. I'm going to suggest we even write this. In fact, when I first started refreshing my algebra skills, I did this to everything to avoid using the quotient rule.
Okay.
Is there any reason I can't write it like that?
No.
Okay, so f prime of x has got to be minus 8 times x minus 6 to the minus 2 times the derivative of the inside, which is 1. In other words, I do have to be aware that I would have a chain rule.
Yeah.
In other words, if that was a 2 in front of the x in the beginning, or a 3, I would have to apply that chain rule. Okay? So now what we're looking at, if I rewrite it in the original format with positive exponents, Notice
Okay.
why that cannot be 0. You can't have something be 0 if its numerator is not 0.
Right.
There is
Is
no
it?
value of x that's going to make this thing equal to 0.
So there are
Whenever
no
you have
points
a
at least.
rational quotient has to be equal to 0, save yourself a step and just set its numerator equal to 0. In other words, if
Okay.
I had something complicated like this, all over something like this, and I said that was equal to 0, is all I'm going to do is set this equal to 0, because that's the only way that quotient can be equal to 0, is if its numerator is equal to 0.
Okay.
Okay? So that
Okay.
proves that there is no place that has a horizontal tangent line. That one of your
Okay.
answers?
That is one of my answers.
No, this
Give me-
is fairly straightforward here. Yeah. Or hyperbolas that are oriented that way do not have horizontal tangent lines.
Okay. So if the numerator doesn't equal 0, then it has no horizontal tangent lines.
That principle applies quite a bit in calculus, where you end up with
Okay.
a quotient equaling 0. Just immediately you know you got to set the numerator equal to 0 for it to have a solution.
Okay.
And it doesn't even matter if the denominator, I suppose it might matter if the denominator were also equal to 0, because theoretically, well, no, the numerator's got to be 0. No two ways about it, regardless of what the denominator is. The numerator has to be 0, yeah.
Okay. That makes sense.
Okay.
Okay. So for the next one, okay, now all of these are going to be related rates.
Okay.
Okay, so let's do this one. A tank of water in the shape of a cone is leaking water at a constant rate of 2 feet cubed per hour.
Hold on, let me make sure I got the shape right. The
Perfect.
vertex is
No.
pointing down.
Yeah.
Guess that's the only way you would build a tank of water.
Yeah.
You could build it the other way, I guess, but... Okay, I'm sorry. What did it say? It's leaking at what kind of rate?
2 feet cubed per hour.
Okay.
The base radius of the tank is 5 feet, and the height of the tank is 14 feet. Then it's asking for, at what rate is the depth of the water in the tank changing when the depth of the water is 6 feet?
Okay. These related rate problems, you almost always want to draw a picture because we have to draw the formula that applies here. Okay.
Okay.
Well, if it's leaking rate at 2 cubic feet per hour, that's a volume. That's a change
Right.
in volume. What that is equal to dV over dt. Okay.
Perfect.
Well, I've got to solve for some of these differentials. But let's start with the formula for the volume of that tank.
Okay.
What is it?
1/3 pi r squared times height.
Uh-huh.
Perfect.
So, they want to know how the water is changing its height.
Yes.
As
So it's
the
looking
leak takes
for...
place. Yeah, because obviously at some point the water is going to go down to there, and then it's going to go down to there. So there's some speed that the water is leaking at, and that is dH dt.
Okay. So
Okay.
that's like h prime technically.
Well, yeah, let's just define it as a differential for now. It makes these related rates problems easier if you define it as a dH dt as opposed to just y prime or something like that.
Okay.
Now, these always used to give me problems, and the reason would be is I would try to implicitly differentiate everything.
That's what I would try and do.
But notice that the only thing they want to solve for is dH dt, right?
Right.
So if I can make this volume a function of h alone, then I will take the derivative relative to time of both sides and I'll be able to solve it fine. Okay? So how do I make it a function of h alone? If I look at this triangle, and then I look at this triangle, they are similar. Correct?
Right. So you can do, okay.
So I can conclude that 5 is to 14
as, what is it, x is to, or 8, or d of h over dt is to 6, right?
Hold on a minute. As x is to y, if I want to call this measurement y.
Right. The height's going to be 6. So then I need to find x.
Hold on a minute. Oh, right. You just came up with it. Because they said at a point when the water level was what?
6 feet, or 6 feet, right.
So when y is 6, correct?
Right. So when y is 6,
5 over 14 is equal to x over 6. And x is my r.
Right.
So I now have x equals 30 over 14.
Okay.
So if I'm still trying to figure out what I'm going to do here. So I guess I can solve this problem since I know that at the point in time they're talking about, my r is 30 over 14. I need to square that, multiply it by my y, which is 6.
Okay.
Now,
that would come with the volume, but that's not...
Hold on a minute. I know how to do these. I just got to remember how.
Right, no, and I like brainstorming going through this with you too,
Yeah,
because
these are the this cone one, for me, is the toughest one of all the related rate problems. The sliding ladder is a piece of cake. The racing cars are a piece of cake. Even the balloon rising, trying to figure out the rate of change of the angle is a piece of cake. But
yep, I cannot agree with you more.
These cones give me a problem. Now, let me go back and take a different tactic and see if it helps.
Okay, perfect.
Let me just differentiate this thing with respect to t. So, first term is 1 dv dt equals 1/3 pi times 2, oh no, I'm going to do it the way I told you. So I'm going to make that r squared times the derivative of
R.
Now hold on a minute. Let's see. If I'm taking the derivative of that, so it's r squared times dh dt.
Oh, I see, I see.
Plus
Plus,
2r dr dt times h. Now, we know what that is. We know what r is going to be when y is 6. We know it's going to be 30 over 14. And we're trying to solve for that. We know what r is, but we don't know what dr dt is.
that's what I'm curious about too.
And we know what the h is at this point. It's a 6, but we don't know what dr dt is. So we've got two variables, and we can't solve it. So back to my original method, which is to try to write this equation in terms of one variable only.
I see. Okay.
Now, r is always related to height. So, right? I mean, x is a function of height based on this triangle. What am I doing wrong over here? 5 is to 14 as x is to y. So x is equal to 30/14, and that is r. So how come it's not a function of h?
That's what I was saying.
It is. It is a function of h. In other words, here's what I need over here. In other words, x is equal to 5y over 14, where y is h, correct? The height of the water?
Right.
So now I'm going to plug that in. Okay, this is the right track.
Okay, so it's 5h over 14 equals x.
Equals, yeah, r in this case. Let's use
that's r.
letters that we have in our formula. So it's now 1/3 pi, and in place of r squared, I'm going to put 5h over 14 squared times h. Okay, now we're on the right track. Because now I can take the derivative of this. I'm going to end up with a dv dt, and I'm going to end up with a dh dt. And also an h. But I'm going to evaluate it when that h is 6.
Right.
So let's do it. Let's dv dt equals
2/3 pi.
Yeah, let me think here. I don't think I need to do the product rule. That's just h third. Here, let's simplify this thing a little bit to make the derivative a little easier.
Okay.
So we got v equals 1/3 pi. Well, that's 25h squared times h. So it's 25h cubed over 14 squared. It's 14 squared. 14 squared is 196.
196.
Okay, so that's what my volume is, as a function of h, always. And in fact, if we go back and we plug in an h of 14, we'll get the volume of that cylinder.
Okay.
Okay, now differentiate both sides with respect to time, because what they gave us was a function, a change relative to time. So now we got dv dt equals pi times 25 over 196h squared.
Okay.
And
okay, I see.
Since
That makes sense.
leakage is 2, should that be a negative or a positive?
Since what is 2?
The leakage.
The leakage.
Should be a negative.
Negative.
In other words, the change of the volume is not increasing. The volume is decreasing. So it's negative 2 equals this thing over here on the right. So let's see. What do we get? We get H. Well, hold on. When I differentiated this thing, I forgot to follow with a dH dt.
Oh, okay.
Okay? So,
that makes sense.
So now we've got minus 2 equals pi times 25 over 196 times h of 6 d squared, excuse me, times dH dt, and now there's only one variable in that equation.
Right. And then there's just a lot of simplification.
Yeah.
Like, what is it? 36 times 196 plus, what is it, 25? And then multiply that by 5.
196 exactly, I think it does, doesn't it? 36 go into 196 3 times?
36 going to 196.
In other words, what I'm going to have is 36 divided by 196.
Okay.
Oh, no. Yeah, it goes in there. Not, what am I thinking? Not 3 times. No, it doesn't go evenly. So I guess you'd have to bring in your calculator at this point.
Right. Yeah, you'd have to. But I know how to do that. That's easy.
Okay. Here, I'll write the final answer.
Okay.
And it's all going to be divided by 36 pi times 25.
Okay.
That's what dH dt is. And notice that it is also negative.
Right.
As it should be. It's reducing in height with time. It's not increasing. It's not getting higher.
That makes sense.
Just like here, if we look at the latter problem, it's really a great illustration of what the signs should be.
Yes, I cannot agree with you.
And that's why, and this ladder is slipping this way.
Right. So that's why
dy dt is negative.
Right.
But dx dt is positive because it's increasing.
Right. I get that, yeah.
Despite the fact that x is moving to the left, for a long time I thought that left meant negative, up meant positive, to the right meant positive, down meant negative. Right. But it doesn't in related rate problems. You have to figure out whether that variable is increasing or decreasing, and that is what determines its sign.
And that's why it's so crucial for you to draw a picture as well.
Yes.
Because you can visualize and kind of interpret
the
problem.
I'll tell you what it is that without a picture, it's hard to write this first formula.
Exactly. Yeah.
And the reason, I guess, this is a unique, it's not a unique, this is a very common related rate problem. The reason it's always given me trouble is this part over here. Finally, I figured out that's what you have to do next.
Exactly. You have to make it one variable.
You have to relate either R to H or H to R.
Exactly.
And differentiate it depending on what it is you're looking for.
Okay. That makes sense. Okay, I get that. Okay. I think we probably have time for maybe one more related rate problem.
Yeah, I'm sure we do. Okay.
Yeah. Okay, so
an angle. Those are always a little hard too. Go ahead.
This one isn't a related rate problem. This one's interesting though. It says find the slope of the slope function of f of x equals 2x minus b to the power of a.
The whole thing to the power of a?
Yeah, the whole thing to the power of a. And then
what they mean, I presume, is the first derivative function?
So no, the slope function of that function is, and then I have another equation. And then it says find the constants AB.
Okay.
So then the derivative function is 24x squared minus 24x plus 6.
Okay.
There we
go. Let's take the derivative of that function at the top.
Is this an integral problem?
I don't think so, no. In other words, we're going to figure out what this is relative to the x's and the b's and the a's.
Right.
In other words, how would I take the derivative of that function in its current state?
I would do like a times 2x minus b to the power of a minus 1 times 2, then you multiply that by 2, and then whatever the derivative of b is.
No, b is a constant. A and b are both constants.
Oh, yeah, that's right. Yep, no, you're right. Yeah.
Yeah. Now,
Okay.
how are we going to equate that to that?
Yeah.
Because I got two constant variables here. I got a b.
Well, those two have to equal each other, don't they?
Well, what has to be true about a?
A.
In other words, if they gave us the final thing and it's a quadratic, then what has to be true about a?
A has to equal 6x.
3.
3?
Uh-huh. Why does a have to equal 3? Because that would make that exponent squared.
Oh,
And
I didn't follow up on the exponent.
Turns into a squared then. In other words, we've got to produce a quadratic since we know the answer. I wouldn't be able to solve this for this quadratic if they hadn't given us the function, because I would add two variables, a and b. But once they tell us it's a quadratic, then it's easy enough to work out that a has to be 3. So now we have a is 3. I've got this 2 over here, so let's go ahead and put that in there. So now we have 6 times 2x minus some b squared all equals that. Well, you can see that we got most of it right, because the 2x squared is going to be 4x squared times 6. That's where we're going to get that 24x.
Okay.
What does b have to be?
B has to be 2.
Think 1.
1?
In other words, if b is 1, then when we square this term, we end up with a constant of 1. And that constant needs to be multiplied by this 6, and that's the only way they got.
Okay, that makes sense.
Okay, so here's our answer. 6 times 2x minus 1 squared. In other words, if I let, and that is assuming a is 3 and b is 1.
Okay.
And now if I expand that out, I get 4x squared minus 4x plus 1. Now if I distribute the 6, I get our answer.
4x squared minus 24x plus 6. That makes sense. Okay.
Actually a pretty interesting problem.
That is. I like that.
I have not seen a problem like that.
And it's more like you have to know functions in algebra and that.
Yeah, in other words, because initially you end up with, gosh, I got two variables here, only one equation.
Right.
Can't solve that. But in this case, because they gave you what the answer was, you know it has to end up being a quadratic, and that'll let you solve it. Okay.
Okay.
All right, we got time for another one if you want.
Yes, sir. Okay. Let's think. Okay. A farmer has 3,200 feet of fencing and wants to fence off a rectangular field that borders a straight river.
Another classic problem.
Yep. Find the dimensions of the fence to maximize the area enclosed by the fence.
This is an optimization problem. I'm glad you gave me at least one of those, because I knew you must have covered optimization. Optimization and related rates kind of usually go back to back. Okay. So the trick on an optimization problem is to first label your model, Okay, well, I like sticking with x's as the horizontal measurements, y as the vertical measurements.
Okay.
Okay, now the function they want you to optimize is the area function.
Right.
What's the area function here?
Like width times height?
With our variables.
Oh, okay. Y times x.
Okay. Now, again, I would normally want to take the derivative of that, set it equal to 0, and solve for it. But I've got two variables here. So we somehow have to relate one of these variables to the other, and I can do that with the 3200 fencing. That's the
Okay.
perimeter of that area. Well, what's the perimeter of that area?
The perimeter is y plus x.
So it's x plus 2y.
Okay.
Now, that allows me to solve for x. X as a function of y is 3200 minus 2y. Okay? That's key because now I can go and plug that in for x, and I will have a function that's totally in y. And then I can take the derivative, set it equal to 0,
Okay.
and solve for it. Okay, so now I have a as a function of y only. So a prime of y equals, well, that's 3200y, so that's 3200 minus 2y squared, so that's minus 8y. Did I do that right? No, I didn't. It's 2y squared, so it's 4y. In other words, I'm distributing first, so I get 3200y minus 2y squared. And then I take the derivative, and that becomes minus 4y.
Okay.
Now, I'm setting that equal to 0. And if you solve that, you get a y of 800.
Okay.
Okay? That means that dimension's 800, that dimension's 800. Total
And
that's subtracted from 3200, that's got to be 1600. And the three-sided objects are always optimized by this shape.
Okay.
By a rectangle that is twice as long as it is high.
Okay.
If I didn't have a river on one side and he had 3,200 feet of fencing and he just wanted to make an area that was the optimum, you make a square. A square is going to give you the maximum amount of area as long as you have to build it with right angles. You could build it with curved fencing. The optimum area is going to be a circle.
Okay.
But it always ends up kind of being what you would imagine.
Right.
Maximize. In other words, you don't end up with shapes like this. Whoops. You don't end up with fences like that, bordering a river, because that doesn't give you very much area. You got area there, but most of your fencing is being taken up with the long measurement.
Right. Right.
So if you find something like that, realize that it's probably wrong. In other words, you want these shapes to be like circles and squares.
Okay.
Okay. But this is like the classic optimization problem, and as simple as they get.
Okay.
Because the function you're optimizing is quite simple, and they give you enough information that you can solve one variable for the other.
Okay.
Once you do that, in other words, you can't, all of these problems, this is kind of similar to the related rate problem with the cone, in that I ended up with a volume function that was a function of two variables, and I couldn't have that. I had to have it as a function of one variable, so I had to use the relationship of the cone to put one variable in terms of the other. And then I was able to proceed with differentiating it, solving for a rate.
Okay.
Optimization problems are very similar, is that you end up needing two equations. You start with the one you're trying to optimize, and then you go looking for any other equation that would let you make either x a function of y or y a function of x. It would not matter. Had I worked this whole problem through an x, then I would have solved for x being 1600, and I would have known y was 8 and 8.
Okay.
All right.
That makes sense. I get that.
So that's the key on optimization problems, is identify your function that you're trying to optimize. That's step one.
Okay.
Okay?
Okay. All right, perfect.
Max, you have a good rest of your day, and I will talk to you next time.
You do the same thing. I am going to go and pay for this session online real quick, okay?
Okay, that's fine.
Awesome. Well, I'll contact you if I need you anytime soon. I have my test tomorrow, so after that, as long as everything goes well, I graduate, so I could not be talking to you until college.
Your final is tomorrow.
Yes.
Wow.
Yes.
Boy, they take them early where you're at. I got a lot of students whose finals not till, well, I guess if seniors take them next week, huh?
Exactly. Yeah, senior is I graduate. My graduation ceremony is next week on Tuesday. So.
Okay. Well, good luck.
Thank you so much. I'm sure we'll be in contact in future as well. It just probably won't be until after the summer.
That's fine.
Awesome. Well, thank you so much, David. I appreciate all the help.
I hope to work with you when you're in college.
Of course. Of course. I would not be surprised if you do.
Okay, Max. Have a good one.
Awesome. Thank you so much. You do the same.
Bye-bye.